called the fundamental theorem of calculus. And it goes with what I would title as a definite integral. And what I mean by that is it has bounds, a and b. So if you think about like this integral from a to b of some lowercase f, and just using it generically, if we don't have a set geometric shape, what we can do is we can integrate it. Let's say the integral of lowercase f is capital F, and we're then going to evaluate it from a to b. The standard notation looks like this. So we've integrated it using the rules, and then we can't forget that we have those bounds b and a. And so we're going from a to b. So what we do is we take the difference of the evaluated integral. So it looks like this. What it essentially is doing is if you have a graph of something, let's just say I have a graph of f here. And if I go from a to b, and that's lowercase f, if I go from a to b, what this is essentially doing is it is taking this space, which is underneath this curve, right? I mean, it's all this space right here that we're calculating. Using the rules and then plugging in the top bound minus the lower bound, what it ends up doing in practical terms is it takes this and splits this into sections, and it really splits it into infinitely many. I'm drawing a finite number, but it splits it into infinitely many and adds up all those sections together. So it adds up all of the green areas. And I'm going to use areas in quotes because it could be negative, but it adds all those up. That's what that process does. If you need more explanation, if that doesn't suffice for you, then I can give you more explanation. But in general, you use the rules that we covered, including if we had to use U-Substitution, and then we plug in the top bound, evaluate it, subtract when we plug in the bottom bound, evaluate it. So what I mean by that is let's take a look at an example. And if you need to rewind this example midway or stop it and kind of gather what's happening, then do that. But if we think about integrating this, we would integrate each individual part. So this is a relatively easy one. We don't have to use U-Substitution. The negative 18 comes along. The x becomes x squared. You divide it by 2. Then minus 3 becomes minus 3x. And we evaluate it from 0 to 1. Now notice we didn't put a plus c on this. Well, the reason we didn't put a plus c is we would end up adding that constant and then subtracting that constant after we plug in these bounds 0 and 1. So we really just don't need a c as long as you're dealing with a definite integral. So an integral that has those values a and b. So in the end, you got negative 9 x squared minus 3x, and we're going to evaluate it from 0 to 1. So now what we're going to do is we're going to plug in that top bound. If we plug in that top bound, we got negative 9 times 1 squared minus 3 times 1 minus negative 9 times 0 squared minus 3 times 0. And we subtract those. So that's that idea of we're doing f of b, the top bound, minus f of a, the lower bound. And then we continue to evaluate it. This one's negative 9 minus 3 minus 0, so negative 12 in this particular case. That's the area. That's the area between 0 and 1 of that original curve. So let's take one that's a little bit more difficult. Take something like this. We don't have a rule for that thing, but we do have a rule. The integral of 1 over u du is equal to the natural log of u plus a constant. We won't need that constant, but so we have that rule that we could use for this. So what we're going to do is we're going to make u equal to 2x minus 1. That means du is equal to 2 dx. That means 1/2 du is equal to dx. So what we can do is we can rewrite this integral using u. We can rewrite this integral as the integral of 1 over u times 1/2 du. Now, one of the things that you need to make sure that you understand is the bounds at the beginning of this problem were x bounds. This was x equals 3 and x equals 8 because that was the variable of integration. But now we're dealing with a new one. We're dealing with u equals. Now, we don't ever label these, and they won't really normally be labeled, but know that those bounds should represent this variable u. Well, notice if you plug in 3 in for u right there, we would get 6 minus 1, which is 5. If we plug in 8 in for there, we would have 2 times 8, which is 16, minus 1, which is 15. So that would really be the integral that we're looking at. We're looking at the integral from 5 to 15 of 1/2 1 over u du. Now we can integrate this. The 1/2 is just a constant. It's going to come along with the integral process. We aren't going to change that. The 1 over u becomes the natural log of u. So if we integrate this, we would have something like 1/2 the natural log of u evaluated from 5 to 15. That bar just kind of says given that we have a lower bound of 5 and an upper bound of 15. So if we continue this, this is 1/2 the natural log of 15 minus the natural log of 5. And the 1/2 is really on the outside because that's a constant that needs to be applied to everything. Now, if you look at this particular thing, it says express your answer as a constant times the natural log of 3. Well, the reason they have it as a natural log of 3 is if you remember from simplifying logs, we could write this as 15 divided by 5, which is 1/2 the natural log of 3. And that's our answer. So that's another way of doing it. But once you change the bounds to u bounds, I never have to go back to x in this case. Unlike when we were doing a U-substitution with an indefinite integral, without those bounds, we went back to x. Now we don't have to because we've adjusted everything to be in terms of u. All right, so now here's one that actually we're gonna need to use U-substitution and not U-substitution because essentially this particular one is the integral from 0 to 20 of 7e to the negative 0.5 x dx minus the integral from 0 to 20 of 1 dx, because we can split that integral into two things. Now, the second one is pretty easy, right? We can integrate that second one. That second one, this one right here, is minus x evaluated from 0 to 20, because the integral of 1 dx is just x. Now, the first one, we're actually going to have to use a U-substitution. We're going to have to kind of take this one and say, well, u is equal to negative 0.5 x. So du is equal to negative 0.5 dx. So negative 2 du is equal to dx if we multiply by negative 2 to get rid of the negative 1/2. So if we rewrite this integral right here, that integral would be the integral of 7 times e to the u times negative 2 du. Now our lower bound is going to be 0, and our upper bound is going to be negative 10. Now the reason it's negative 10 is we would plug in 20 in for x into this u right here. And if we plug in 20, we'll get negative 10. When we plug in 0, we get just 0. Now we can integrate this. We don't have to go back to x. We'll deal with all these separately. But this one then is negative 14 e to the u. The integral of e to the u is just e to the u, evaluated from 0 to negative 10, minus, and we still have x evaluated from 0 to 20. Notice we have two variables, but that's okay because our bounds are within reason of those two variables. So we're going to keep on evaluating this. And if I evaluate this one more time here to plug these bounds in, I'm going to do it way over here on the side. I got negative 14 e to the negative 10 minus negative 14 e to the 0 minus 20 minus 0. So I just plugged in those bounds in for each of those variables, and I did subtraction. So simplifying this, I got negative 14 divided by e to the 10th plus 14, because e to the 0 is 1, minus 20 plus 0. So in the end, I got negative 14 over e to the 10th minus 6. And that would be my answer. Now, I know that that one has a lot going on, so maybe go back and watch that one, that example again if you struggled with where I got things, because I know it might have been hard to write it down and watch it at the same time. All right, let's take something like this one. Same kind of deal, only this is a U-substitution problem. You know, if I kind of think about this, I could bring out the 5/2. That is not part of this integral, and I could make this 4x minus 7 to the negative 3/2 dx, and we still have the bounds 2 and 4 because I haven't changed them to u yet. But now I can do a u substitution on this. I can say u is equal to 4x minus 7, so du is equal to 4 dx, so 1/4 du is equal to dx. I'm just going to have that 1/4 with me. So if I rewrite this integral, this is going to be 5/2. The integral, I'll deal with the bounds in a second. Hopefully you kind of know what I'm doing with those bounds. I have u to the negative 3/2 times 1/4 du. Now let's deal with those bounds. Notice here's u. These are x equals 4, x equals 2, and x equals 4. So now we want u. When x equals 2, u is equal to 1. 4 times 2 is 8, minus 7 is 1. 4 times 4 is 16, minus 7 is 9. Now, if I have this, now my bounds are in terms of u. I can go through and I can integrate this. I have negative 5/8 because that 1/4, I'm just going to put that 1/4 and the 5/2 together. This would be u to the negative 1/2, because negative 3/2 plus 1 is negative 1/2, divided by negative 1/2, evaluated from 1 to 9. So let me keep going with this. Deal with these constants. Notice I have two negatives there. This is going to be 5/4. There's 1 over u to the 1/2 evaluated from 1 to 9. So now if I plug in my bounds, plug in those bounds, I still have that 5/4. I have 1 over 9 to the 1/2 minus 1 over 1 to the 1/2. And in that case, that's 5 over 4 times 1 over 3, because 9 to the 1/2 is 3, minus 1. So 1 to the 1/2 is 1. And then I've kind of run out of room, but the rest is just arithmetic. Hopefully that makes sense to you. Okay. So let's let me stop there, and I'll create a new video for the last couple of examples here. So I'm going to give me a second to stop the video.